In this lecture, so second lecture out of chapter 14, so here we'll look at how to synthesize ethers and how to synthesize sulfides. So we've talked about one way to synthesize ethers in a previous chapter. So you can synthesize them from primary alcohols by reacting them with sulfuric acid, and then that would make this, so take the ethanol, that would make the diethyl ether. So predicting the product is easy, right? If you see a primary alcohol and sulfuric acid, then again, if you just learn to recognize, so basically remember reagents and recognize reactions, predicting the product is easy. If you remember this reaction, you just lose a molecule of water, and then this ends up attached to there, and you have this ether, right? So that's the easy part. The harder part is knowing the mechanism. So how does this reaction work? So we've talked about the mechanism before, but we'll go through it again. So sulfuric acid, anytime you see this, you can think of it like an H+. It just donates a proton because it's a very strong acid. So basically what happens is oxygen from the ether can take the hydrogen off of sulfuric acid, and the OH electrons become a lone pair on oxygen. So then that would give you this, and HSO4 minus conjugate base. And so now you basically have a good leaving group on the carbon because you have a water molecule sitting there. So you can, so another alcohol can react. So take a lone pair from another alcohol, and that can attack this carbon, and that can kick off a water molecule. So the electrons in the carbon-oxygen bond then will become another lone pair on oxygen. So you have a water molecule that leaves, and then you would have this, right? And then the last step in this mechanism, so HSO4 minus that you lost in the previous step can come back in and take a hydrogen off, and the OH electrons will become a lone pair on oxygen, and now you have the ether, and you got your H2SO4 back. So you use the H2SO4 to get this reaction going, so that facilitated the reaction, made it faster because it converted OH, which is a poor leaving group, and it converted it into H2O, which is a good leaving group. So this is easier to displace, so that reaction can occur faster. So the H2SO4 sped up the reaction in that sense, but in the end you got it back, so it's not consumed, so that means it's a catalyst, right? So you don't need a lot of H2SO4 for this, just a drop or two to get the solution acidic, and then the reaction can occur. Okay, so this is a good way to make symmetrical ethers, but it's not a good way to make non-symmetrical ethers. So for example, if you tried this reaction, if you took propanol and ethanol and you wanted to make that ether, which is non-symmetrical, you could make that by losing the water molecule, right? But the problem is you would get other ethers formed because two propanols could react with each other, right? And you can make dipropyl ether, or two ethanols could react with each other. And you would make diethyl ether. So you can make diethyl ether, dipropyl ether, or you could make ethyl propyl ether. So you would get a mixture of all three, and you would expect to get about a statistical mixture. So you would expect around a 33% yield of each. You know, so that could be fine if you have cheap starting materials, but then you have to separate these, and that takes a lot of time, and that takes energy, which means it costs money. So if you want to synthesize a non-symmetrical ether, there's a better way to do it that will boost the yield and it'll minimize side products, which means it makes the purification easier, which means it's a cheaper process overall. And the way to do that is to do what's known as a Williamson ether synthesis. Okay, so the way that this works is you would take an alcohol and you would react it with a strong base to deprotonate the alcohol. So butyllithium would be an example. We haven't talked about this before as a base, but it's a very strong base because carbon's partial negative, right? Lithium's partial positive. So this carbon can use these 2 electrons to make a bond to that hydrogen, and then the OH electrons become a lone pair. All right, so now that oxygen has 3 lone pairs, so it's negatively charged, and lithium would be the cation, and then you would make a molecule of butane. So if butyllithium carbon takes a hydrogen, now you have butane, which is a gas, and it would just bubble out of your solution. So now you have the conjugate base of the alcohol, so that would be what's called an alkoxide. And the significance is that it's a strong nucleophile. So then the oxygen here can now attack that carbon and kick off the bromine, and that's an SN2 reaction, and you would make butyl ethyl ether, right? And there is zero chance of making dibutyl ether, and there's zero chance of making diethyl ether. The only ether that you could make would be the butyl ethyl ether. So you would expect a very high yield of that with minimal side products that you have to purify from. So you basically deprotonate the alcohol with a strong base, creates a good nucleophile, an alkoxide, that then you react with something that has a good leaving group on it, and that will do an SN2 reaction to make the ether. So we've talked about other ways to deprotonate alcohols in previous lectures. So chapter 10, so back to organic 1. So you could use NaH, sodium hydride. So H- is a good base. It can take off that hydrogen, and the OH electrons become a lone pair. Right, so you can make that alkoxide, which is a good nucleophile that you could use for an SN2 reaction. Or we've looked at you could just use a group 1 metal. So lithium, sodium, potassium, cesium. So we won't go through the mechanism here again. You can refer back to chapter 8 or 10 video if you want to see how this reaction works. So if we use sodium, for example, then that would just make the sodium salt, and you would make H2 gas. And the same in the first, when H- takes off H, you would also make H2 gas, which will bubble out of your solution, and then you would just have the conjugate base of the alcohol, the alkoxide, sitting there. Or we looked at that you could use butyl lithium to deprotonate the alcohol. Okay, so once you have the conjugate base of the alcohol, then you just react it with something that's got a good leaving group, so like chlorine, like bromine, iodine, or tosylate. It could be a tosylate. So oxygen will attack carbon, kick off a chlorine. And the rest of the carbons are just along, so that's just along for the ride, right? You make a bond from oxygen to carbon, and whatever's attached to carbon is just along for the ride. And so in this case, you would make that ether. Okay, so since this is an SN2 reaction, the alkyl halide, you remember, should be methyl primary or secondary, because SN2s don't work with tertiary alkyl halides. So if you remember, the rate of an SN2, methyl reacts faster than secondary, reacts faster than tertiary. And tertiary in general does not work for SN2 reactions. So whatever you're reacting the alkoxide with should be a methyl primary or secondary halide or a tosyl group there. Okay, so let's use this. Let's do a synthesis problem. So make this ether using a Williamson ether synthesis. So you should know the name. You should know what that means. What does Williamson ether mean? Synthesis. So that means you're going to have an alkoxide and an alkyl group with a leaving group on it. So that means we can consider splitting this up either here, so we'll call that A, or we could split it here, and let's call that B. So if we undid bond A, then oxygen would then be would have been negative, so that would have been your alkoxide, and then your alkyl halide would have to be this piece, so you'd have to have a leaving group there, whatever the leaving group is. All right, so it could be OTS, could be iodide, bromide, chloride. But this is not going to work, right? Why is this not going to work? Because that is tertiary, and so this can't do an SN2. Because this would need to attack that carbon and kick this off, and that's not going to work because it's tertiary. So you can't undo bond A. You have to undo bond B instead. So if we undid bond B, then this carbon would need a good leaving group on it. So whatever you want to put there, chlorine, fluorine, chlorine, bromine, iodine, or a tosyl group, and then your alkoxide would be, in this case, tert-butoxide, which we've seen before as a good base, but it can also serve as a nucleophile. So then this could attack here and kick the chlorine off, and that would work to make this ether. So in this case, there's only one way to do a Williamson ether synthesis to make that particular ether. Okay, and so in terms of sulfides, so making sulfides is similar to a Williamson ether synthesis. You would just start with thiol, and if you remember, the hydrogen of a thiol is relatively acidic, so you just need a base to deprotonate it. But thiols are more acidic than alcohols, so you don't need as strong of a base. Sodium hydroxide is a strong enough base to do the job. So if you react this with hydroxide, OH minus will take that hydrogen off, and the SH electrons will become a lone pair on sulfur. And so now you have a very good nucleophile. If you remember our S minus from chapter 6 in organic 1, that's a good nucleophile. So this can do an SN2. So now S minus can attack carbon and kick bromine off, and that's an SN2 reaction. So you would make whatever's attached to sulfur is just along for the ride. All right, so you would make that sulfide. So if we did this synthesis, so if you see sequence like this 1 and 2, that means you do 1 first. So whenever you see NaOH, you should recognize it's Na plus OH minus. So take a lone pair on oxygen, take the hydrogen off of sulfur. So now you have an S minus, and its conjugate, and its cation would be Na plus, but the sodium's not doing anything, right? It's just a spectator ion. And then you take that and react it with the alkyl halide. So sulfur will attack here and kick the bromine off. And you would make that ether. So that would be what? 2-methyl propyl. So methyl, 2-methyl propyl sulfide. Okay, so that's how you make sulfides and ethers.